Hello, welcome to the 4-H Level 1 Junk Drawer Robotics course. My name is Joe Bartlett, and I'm going to be your advisor for this class. Just a little bit about me. I went to school at the Missouri School for Science and Technology, and I majored in mechanical engineering. Of course, when I went to school there, it was still called the University of Missouri at Rolla. I have a fair amount of engineering and technology background. Most of it is automotive related. One of my favorite hobbies is to help my friends work on their dirt late model race cars. So that's where I spend a lot of my free time. I have two daughters that are in 4 H. I really enjoy helping them do their projects, and I'm happy to be here. And I hope I can pass a little bit of my engineering knowledge along to you. In this course, we're going to use the book provided to us by the 4 H Extension Office. If you'd like to get a copy of that book, feel free to contact the Extension office or you can find one online. However, you don't need that book to take this course. Anything that we need out of the book, I will read in the video. However, if you'd like to get one and you want to spend the money on it, go right ahead. It might be nice to follow along, but you absolutely don't need it for this class. There are a few things that you are going to need for this class, though. First off, as the name implies, this is a junk drawer robotics class. So later on in this course, we are going to be building a few different things, and we're going to build those out of common household items. For example, things you might find in your mom or dad's junk drawer. Now, they don't have to be in the junk drawer. They can be anything that you have around your house. So get creative and maybe start gathering up some different things that you might use to build robots or other things. For example, popsicle sticks, yarn spools, anything of that nature. Gather all those things up and put them in a box and keep them for later because we're going to use those to build your projects. Now, the second thing you're going to need is a notebook. Now, you can find notebooks kind of like this at your local Walmart or Target. But if you don't want to go buy one, any old notebook will do, or even just a couple of sheets of paper. But what I'm going to want you to do is throughout the course, I want you to take notes because that's something that engineers do all throughout their careers. And so that's what we're going to do is we want to take good notes about what we're doing and we want to track our process, but we also want to track our thoughts and ideas so that we can come back to those at a later time. So get with your mom or dad or guardian and have them help you find or go buy or make a notebook that you can use to take notes throughout the course. Now, before we get started, one thing I want for us to do is get your notebook out and I want to ask you a question. I want you to tell me and write in your notebook what you think a robot is. Now, pause the video and get your notebook out and just write that down on the first page. Doesn't have to be anything real extravagant or real detailed. Just write what your interpretation as of today, right now, what you think a robot is. So, a robot is a mechanical device that sometimes resembles a human and is capable of performing a variety of often complex human tasks on command or by being programmed in advance. So that is the Hermitage Dictionary definition of a robot. It can also be defined as a machine or device that operates automatically or by remote control. So you may have seen on TV, sometimes you think of a robot as something that looks like a human being or something that has arms and legs. That's the type of robot that you would typically see in the movies. But in reality, most robots look like what we see in the picture in the lower right. Doesn't look anything like a human being, does it? But this robot is used typically in industrial applications to do work, oftentimes work that would be really dangerous or really monotonous for human beings. And so we design and develop robots to perform that work so that human beings don't have to. So now that you've got your definition of a robot written in your notebook, we're going to go through this class and hopefully you learn something about robots. And at the end of the class, I want you to write that same definition in your notebook, and I want you to compare what you originally thought a robot was to what you would now think a robot is. So at the end of the class, that's something we'll do, okay? So before we get started, I want to go over a brief outline of what we are going to do throughout this class. This course is going to be broken up into two modules, and within each module, there are three sections: a to learn section, a to do section, and a to make section. In the first module, in the to learn section, we're going to do activity A, which is called Think Like a Scientist, activity B, where we're going to learn to communicate like an engineer, and activity C, where we will learn to build like a technician. And then in the to-do section, we're going to design a catapult that will launch a marshmallow. And then in the to-make section, we're going to build that catapult. Module 2 is called In Arm's Reach. In the to-learn section of Module 2, we're going to do activity F, called A Sense of Balance, activity G, called ABC XYZ, and so we'll get into the details of those activities later on. And then in the to-do section of Module 2, we are going to design a robotic arm and gripper mechanism. And then in the to make section of Module 2, we're going to build that robotic arm and gripper mechanism. Okay, so let's get started on Module 1. So in Module 1, our main focus is going to be to talk about the difference between what a scientist does compared to what an engineer does and compared to what a technician does. So in activity A, we're going to talk a little bit about what a scientist does. So if you think about what a scientist does, a scientist is really focused on learning about new things and trying to come up with better ways to do things. So they do a lot of laboratory experiments. So sometimes when you watch TV and you see people walking around in lab coats and working in laboratories, those are scientists. And scientists typically do experiments and very well thought out and planned experiments to test new ideas, often called hypothesis, and evaluate different ways and better ways to do things. And in the process of doing this, scientists have to document their findings. Once the scientists have performed their experiments and collected their data, they oftentimes store this data in tables, and these tables can be referenced by other people. Let's take a look at some examples. In mechanical engineering, we're often interested in how strong a particular piece of material is. For example, a piece of steel or a piece of aluminum. And so scientists will work in laboratories and test different types of materials to see how strong they are. So in this table, for example, we see various types of steels, and along with each type of steel, we see the tensile stress, which is the amount of stress we can put on a material before it breaks. We see the yield strength, which is the amount of stress that we can put on a piece of material before it starts to deform, and a few other things, percent elongation, for example, all found within this table. And so, one of the things that a scientist does is they build these tables so that other people have that information to use. So, there are all types of tables that scientists put together. For example, another table commonly used in mechanical engineering is a table that shows material geometry. This table, for example, shows us the geometry of structural angle iron commonly used in industry. It shows the length of each of the legs of the angle as well as the weight per foot. So, one of the key takeaways after looking at these tables is to understand that scientists conduct research and log and record that research so that other people can use it. So that's what we're going to do in our activity A of thinking like a scientist. So I want you to start looking around your house and finding different pieces of material that you can use on your projects. And then we are going to document all of those things that you found. And what we're going to document is the form and function of the parts that you found. So, what is form and function? Well, form is what we refer to as the properties of the material. So, for example, its shape, its weight, its appearance, and the function of the materials that we're going to use are going to be what we think we might use those things for. So, for example, if we had a popsicle stick, the form of this popsicle stick would be that it's green, that it's about 6 inches long, maybe 3/4 of an inch wide, and about an eighth of an inch thick. Its function would be that we might use it as a lever or maybe as a structural member. So get creative about the things that you think you might use your material for. So here's another example, a smaller popsicle stick. Here's an example of a small pipe cleaner. So again, its form would be that this is purple. It's about a foot long. Its function might be that we might use it as a rope of some kind, maybe, or we might use it as a fastener where we could tie two pieces together. Again, get creative. And what I want you to do in your notebook is make a table showing the form and function of all of the pieces that you found. Now, when you do this, I want you to imagine that you are going to have to hand this table off to someone who has to build your project but hasn't ever seen any of the materials that you have. So you want to be thorough enough in your table to describe all of the materials that you have available so that someone who's never seen that list of materials would be able to know what they have to work with to build the project. So now that we have learned how to think like a scientist, we're going to move on to activity B and talk about how we can communicate like an engineer. So, what does an engineer do? Well, an engineer is a person who takes research and data generated by a scientist and he or she applies that information into designs. And typically, those are designs that solve some kind of real world problem. For example, a mechanical engineer might design a robotic arm that is capable of lifting a certain amount of weight. So that engineer would reference the tables generated by the scientist to find a material that has the appropriate properties to support the load that they are trying to support. That engineer would also have to calculate the size of the material necessary. So once the engineer has performed all of those calculations and completed the design work, he or she has to communicate those ideas and those designs to other people. The engineer does this by the use of engineering prints. And so that's what we are going to do in Activity B, where we learn how to communicate like an engineer. We're going to practice making a 3-view print. So what is a 3-view print? Well, a 3-view print is a print that shows an object from 3 different viewpoints. Typically, these viewpoints are viewed as if you were on top of the part, a view if you were looking at the part from the front, and a view as if you were viewing the part from the side. So what I want you to do is to walk around your house and find an object to make a print out of. Now, I wouldn't find something that's too complicated, but you also don't want something that is symmetrical across all 3 of those views. So for example, what I have here is a battery off of a cordless drill. And so if I were going to make a print out of this, I would make one view of the print as if I were looking at it from the front. A view as if I were looking at it from the side. And a view as if I were looking at it from the top. So here's an example on the slide of a 3-view print. Here we can see an object that has 3 views, and each of the views has dimensions. So after you sketch out each of the 3 views, find a measuring device, like a ruler or a tape measure, and measure out the different dimensions of the relevant features on that part. So if I were going to measure this, I would measure the width, probably, the thickness, the height, how wide it is here. And then on the top view, I might give a dimension for how wide it is here, and so on and so forth. So once you have made a print, I want you to bring that print with you to our first in-person meeting. But don't tell anyone else what your print is a print of. We'll pass the prints around to each other, and we'll play a game where we try to guess what each of us drew in our print. So when you make your print, try to make it detailed enough so that other people can figure out what you drew, and also so they can figure out dimensionally how big the item is. So at this point, we have learned how to think like a scientist and communicate like an engineer. Now we're going to move on to Activity C and learn how to build like a technician. So now that an engineer has a design communicated on paper, someone has to take that design and convert it into a real world product. And that is what technicians do. Technicians take designs produced by engineers and build the projects that the engineers have designed. So how do technicians build the products that the engineers designed and documented in their prints? Well, they use manufacturing processes to convert raw materials into finished products. So what are raw materials? Well, if you've ever walked through your local Lowe's or Home Depot and seen those big stacks of lumber, well, that lumber is a form of raw materials. So a technician can take that lumber and modify it and work it into a final product. Another form of raw materials might be that piece of angle iron that we looked at in Activity A. So that angle iron comes in a raw material form, and technicians can take that material and form it and use it to build a final product. And so, what are some of these manufacturing processes that technicians use? Well, we do things like separate and cut material. So, if you've ever been in your mom or dad's workshop or garage and you've used a handsaw to maybe cut a piece of wood, that's a form of manufacturing. So, you've taken that piece of wood and you've modified it and turned it into something else. We also use manufacturing processes to shape wood or shape material. So, for example, if you've ever drilled a hole in a piece of material, that's a manufacturing process. If you've sanded a piece of wood or filed a piece of metal, that's a manufacturing process. We also can use big, heavy machines like lathes and mills to what we call turning metal to shape and refine that material. We can also use methods like to bend and form material. So, oftentimes with sheet metal, for example, we will bend that material to convert it into a final form. And we also use methods to join and fasten materials. So, again, if you've ever nailed two pieces of wood together, that's a manufacturing process. We can also glue or epoxy materials together. We use screws and bolts. I'm sure you've used some of those a time or two. But we can also use methods like welding to join metal or plastics together at the atomic level. So there are all kinds of manufacturing methods that are used in industry. So can you think of some other methods that are used? Why don't you write those down in your notebook and bring them to our first meeting and we can discuss them? So, what we're going to do now is we're going to talk a little bit about what are the best ways that we can join material to accomplish a given goal. So, what I'm going to have you do is perform a little experiment on your own. And then when we come together in person, we're going to discuss your observations. So, what I want you to do is get some popsicle sticks and I want you to build two shapes. One is going to be a square and one is going to be a triangle. Now, when you join these popsicle sticks, I want you to join the ends so that they're in a pinned fashion. So, what are some different ways that you could make a pinned joint? Well, a couple of things that you might be able to do is maybe take a paper clip and bend it out so that it's straight. And then you could drill a hole in the ends of the popsicle sticks and used the metal part as a pin. Now get your parents to help you when you're cutting these pieces. And also be very careful that if you're dealing with anything with a sharp edge, that you don't poke yourself. And it would probably be a good idea too if you're cutting materials to make sure you're wearing eye protection. So another way that you could make a pin joint is to maybe use one of these brass tacks. So these are commonly used in notebooks. They are a one-piece brad that has two little wings that you can bend out. And so you could use that as a pinned joint. Or you might use a pipe cleaner that you could poke through a hole and bend around. Similarly to using the paper clip, use that as a pinned joint. Or get creative if you can find another way. I just want to make sure that the joint can swivel. And so I want you to build those two shapes, and then I want you to make observations about what you see with the shapes. What do you observe? So play around with it and write down in your notebook your observations. Bring those to your first meeting and we will talk about what you observed. Our next activity, activity D, is going to be to build a trebuchet that will launch a marshmallow. So you may ask, what is a trebuchet? Well, a trebuchet is a mechanical device that uses a weight and some lever arms and a sling to throw an object. So our trebuchet is going to have a couple of design requirements that go with it. First, it must be of a trebuchet style. So you can look in the picture on the screen and that gives you kind of an idea of what a trebuchet looks like. I'll also put a link in the description below to a video that I posted that shows a trebuchet that my daughters and I built, and it was a trebuchet model kit that we bought from Hobby Lobby, but it shows the general operation of how a trebuchet works. So feel free to have a look at that video. The second requirement of the trebuchet is that the arm needs to have an adjustable point from center to center. So the fulcrum, or the point where the arm rotates, needs to be adjustable. The third requirement is that I want you to try to use at least 5 different materials in your design. Fourth requirement is that it must use weights and gravity as the power source. So that's a pretty easy one since that is a general description of a trebuchet anyway. And the last requirement is that it must be capable of launching a marshmallow at least 6 feet. So the marshmallows I'm talking about are not the little marshmallows. These are the marshmallows that you might use around a campfire. Let's take a look at how a trebuchet works in a little more detail. So a trebuchet is got a lever arm with a pivot point in the center, as you can see on the picture to the far left. And it has a weight, and a weight is supported in some kind of a basket or attachment. And that entire arm is connected to some type of a frame mechanism that can support it. And there is a sling attached to the opposite end of the arm, so opposite of the weighted side of the arm. And one end of the string of that sling is connected to the frame permanently, while the other string is free to slide on and off of a pin. So if you notice in this picture, on the end of the arm, there is a small pin that sticks out. And so as the trebuchet is activated and the weight pulls the lever arm down, as that sling spins around, one half of the string will come disconnected from the lever arm, and that's what allows the trebuchet to release the weight that it's trying to throw. And so this picture shows a general operation of the different points of how that trebuchet works as the weight is released. Let's take a few minutes and talk about something called the engineering design process. Now, when we sit down and come up with a design for our trebuchet and we start to build it, we don't want to just randomly start building things without a plan. And so what we do is we use a design process, which is a methodical workflow that we go through and follow as we design our projects. Let's take a look at that design process in a little more detail. As you can see on the graphic to the right, this process is circular in nature. It starts by identifying your problem or your need or constraint. And so we've already done that with our trebuchet project where we talked about the design constraints of our project. The next step, going clockwise on this graph, is to research the problem. So we kind of did this a little bit already where we talked about the general design and function of a trebuchet, but I want you to do your own research too. So get a parent or an adult to help you go online and search for trebuchets. And I want you to try to see if you can learn even more about how a trebuchet works, where they've been used, and maybe when they've been used throughout history. And so you have a better understanding of their purpose and where they've been used. Once you've done your research, the next step is to start coming up with some ideas for how you want to design your trebuchet. So this is where in your mind you start thinking about some different concepts. And this is also where you would start to sketch your ideas out inside of your notebook. Now, these sketches don't have to be the 3-view sketches like we did earlier in the video. These just need to be some general sketches that you can use to document your ideas so that later on you can come back to your notebook and be reminded about the ideas that you came up with. Once you have maybe 2 or 3 different concepts, you can start to list the pros and cons of each one of those concepts. And once you've done that, you can eventually come up with which design you think is the best out of all of your concepts. And so once you come up with a final design, you can build a prototype of that trebuchet just to test your ideas and test your design. Now, you don't have to build a prototype if you don't want to, but generally in industry, whenever we design things, we build a prototype. And oftentimes that prototype is built out of some cheaper materials. Maybe we cut corners on a few things here or there. Really, the main purpose of a prototype is just to test and validate your design, just to make sure that it works the way that you think it's going to. So with your trebuchet, maybe you could just make a simple mock-up just to test the functionality of the trebuchet, just to make sure it's going to work. And in the process of doing that, you can identify any modifications that you might need to make. And then that's where the circular functionality of this design process comes into play, because as you identify problems in your testing, you can identify future needs, research possible solutions for the new problems that you found while you were testing, make the changes, build another prototype, test and evaluate, and do that over and over again until you come up with a final concept for a product that you want to make. And then once you have come up with that final design, you really need to think about, okay, what type of things do we need to communicate about our design? And so this is where you would make a print of your final design. And in that print, you need to talk about possibly what materials are going to be used, how are you going to assemble the materials, what fasteners are you going to use, any other details about your design. You would put all of that on your final print. And again, don't forget to document this stuff. Include all of these things inside of your notebook. So at this point, you should be ready to start designing your trebuchet. Just to help move you along, here are a few pictures of some things that other people have done. Now, don't copy these. You need to make your design your own, but at least these will give you a little bit of an idea of what other people have done in the Junk Drawer Robotics course. So this is the end of the first session. Later on, we'll have an in-person meeting where we'll come together and build your trebuchet. So have your print ready to go and all of your materials ready to go when you come to the in-person course. And we should be able to hit the ground running as soon as we get there, and we'll be able to spend all of the time building because you will have already had a good print and a plan in place for what you want to build. So after we're done building the trebuchet, a few questions you can ask yourself and maybe jot down in your notebook is what shapes worked well for the design and what shapes didn't work well for the design. So what materials and shapes of materials did you use and how well did those things work? What are some other ways that the catapult could have been made? How could different catapults be classified into different groups? So if you were to build multiple types of trebuchets, how would you classify those? And the last thing to ask is go back and think about how hard this process would have been if you didn't have a good print and a good set of instructions to work off. Think about how chaotic that would have been if you would have come into the in-person meeting with no plan in place or no idea of what you were going to do. Now that we're done with Module 1, we'll move on to Module 2. We'll start with Activity F, a sense of balance. In this activity, we're going to talk about torque. So what is torque? Torque is a rotational force that's caused by placing a force at a given distance from a fulcrum. So what is a fulcrum? Well, a fulcrum is a point where a beam rotates around. One example of this might be when you use a wrench to turn a bolt or a nut. So when you use a wrench, you place one end on the head of the bolt, and that is essentially the fulcrum. And then we apply a force at some distance from that fulcrum, and we rotate the wrench. That force or that twisting motion is what we call torque. So if I were to grab a hold of the end of that wrench and turn the wrench, you can see how that's going to act to move my hand in a rotational fashion. So that is what we call torque, is that rotational force. Another concept we need to talk about is force equilibrium. So when we have two forces that are equal but opposite to each other in direction, or torque in this case for what we're talking about, when those forces are equal to each other, they cancel each other out. And we call that force equilibrium, or in other words, a force balance. So those two opposing forces essentially cancel each other out. So if we look in the diagram on the right, we see a beam that is balanced on a triangular shape. So this is very much the same concept that we see on a playground when you're sitting on a teeter-totter. In the diagram, we can see that that beam would be in balance when the two torques generated by the force on the left versus the force on the right are in equal but opposite directions. When this happens, we say that the torques are in equilibrium with each other. And each of those torques are generated by the force applied to the beam multiplied by the distance from the fulcrum to where that force is applied. And when those force times distance values are equal and opposite of each other, we say that the system is in equilibrium, or in other words, that the system is in balance. So remember, the equation for torque is a force times the distance from a fulcrum. So in our teeter-totter example, the force would be your weight. So let's say you weighed 100 pounds and you were 5 feet from the fulcrum of the teeter-totter, or the point where the teeter-totter was rotating about. So the torque generated by your weight would be 100 pounds times 5 feet. So the torque would be 500 foot-pounds. And so the units for torque are foot-pounds. Or in other words, a unit of weight multiplied by a unit of distance. So in this exercise, I'm going to give you a table that has 8 different weights and distances provided to you. I want you to calculate the torque generated by those forces and distances. And in this table, the force is provided to you in ounces, and the distance is provided to you in inches. So your torque units in this case would be ounce inches. And once you've calculated those torques, I want you to come up with a weight and a distance that will keep that torque in equilibrium. Now keep your distance within, say, 9 inches or so. And in our second in-person meeting, we will do an experiment and we will test your calculation results and see if the force and distances that you came up with will keep the beam in balance with the force and distances that I provided to you in the table. And we'll do that for each of the 8 different scenarios that are provided in this table. In Activity G, we are going to talk about coordinate systems. So what is a coordinate system? Well, a coordinate system is what we use to define a point in three-dimensional space to describe where an object physically exists. It is a coordinate system that we use to tell robots where to move to, and we do that in the software program that drives the robot. So there are 3 different types of coordinate systems that engineers typically use. The first is called a Cartesian coordinate system, and this coordinate system consists of 3 numbers. The first number in this coordinate system defines where an object exists relative to an origin point along an x-axis. The second point describes where that point is relative to the y-axis. And the third point is what describes where the point is relative to the z-address. There are other coordinate systems as well, such as the cylindrical coordinate system or the spherical coordinate system. Now, these 2 systems are a little more advanced than what we're dealing with, so what we're going to focus on is just the Cartesian coordinate system. So if you look at the graph on the right of the screen, you'll see an example of an XYZ coordinate system. And you see a point where all 3 of those X, Y, and Z axes intersect, and we call that the origin point. And so this is the point where we measure all of the other points relative to. And this origin point has an address of 0, 0, 0. And so as you can see, the point in that graph, if we were to define its point relative to the origin, we would measure along the x-axis to get the x-coordinate position. We would measure along the y-axis to get the y-coordinate position. And we would measure along the z-axis to find the z-coordinate position. Now, one thing you'll notice is when we make those measurements, the measurements have to be in parallel with the axis that we're measuring along. So we don't want to make any angular measurements. Everything has to be square when we take these measurements. So what we're going to do for an activity in this section is I want you to find a room in your house, maybe your living room, and pick a corner of that room, and we will define that as the origin point. Then I want you to pick an object out of that room. We're going to measure the Cartesian coordinate position of that point. So maybe pick the corner of your couch, maybe. And I want you to measure out and find what the three-dimensional address is of that point. So how would you do that? Well, if you put your origin point at the corner of the room, then you could pick one wall to be the x-axis, another wall to be the y-axis, and then we could define the z-axis as being the distance from the floor. And remember to keep your measurements perpendicular to the walls. And when you do your x and y measurements, your point is going to be at some distance off of the floor. So imagine dropping a plumb bob down from your point to the floor, and then your x and y dimensions will be measured on the floor, and then the z dimension would just be from the floor up to the point that you want to measure. And so at that point, you now have an x coordinate, a y coordinate, and a z coordinate. So if you wanted to communicate this position to another person or to a robot via a software program, you would define that point using those three-dimensional Cartesian coordinates. So in industry, that is how we program robots and tell robots where to go. So for example, if we wanted a robot to pick a box up from one position and move it to another position, we would define the initial position of that box using a three-dimensional coordinate position, and we would define the point that we wanted to move the box to with a second set of three-dimensional coordinate positions. Robots can use any one of these coordinate systems, the Cartesian, the cylindrical, or the spherical, or a combination of any of those three. Let's take a look at some different robots that utilize these different coordinate systems. Here are some robots that utilize the Cartesian coordinate system that we've already discussed. As you can see on these robots, they have mechanical joints that move the robot parts in each of the X, the Y, and the Z coordinate system. We also have a spherical robot, in which we didn't talk too much about that coordinate system, but you can see the difference in how this robot moves compared to the Cartesian coordinate system. As you can see, it rotates about a single point and then has an arm that moves up and down. And we also have robots that use the cylindrical coordinate system. Again, we didn't talk about it too much, but you can look at these robots and see how this type of robot has a body that swivels back and forth rotationally, and then the entire body can move up and down on the z-axis. And then we also have a jointed robot, which is really a robot that uses all three of these type of coordinate systems. So there are many, many different configurations of robots, not just the pictures that we've seen so far. Why don't you have one of your parents or a guardian help you look up online different types of robots and see if you can find some different configurations. So one of the things that all of these robots have in common is they have different parts in the assembly that move relative to each other. So what allows those different parts to move is the utilization of what we call joints. And so joints are what allow two different bodies to be connected but still move relative to each other. So when we talk about movement, oftentimes in engineering, we talk about what is called a degree of freedom. So when we look at a given body or a part, we often say that that part, if it doesn't have any kind of joint constraining it, we say that it has 6 degrees of freedom. So what does that mean? Well, let's take this block, for example. If I don't have anything constraining the movement of this block, it would have 6 degrees of freedom. So what are those 6 degrees of freedom? Well, This block can move up or down. It can move left and right, or it can move in and out. And in engineering, we call that translation or just inline motion. So that's 3 of the degrees of freedom. The other 3 degrees of freedom are what we call rotation. So this block is also free to rotate in one direction. It can rotate in this direction, and it can rotate in this direction. So that completes the 6 degrees of freedom of this block if it doesn't have anything constraining its motion, right? And it can move around in space all over the place. And so if we were designing a machine, we would use joints to join pieces together, but also to restrict a body's range of motion or restrict its degrees of freedom. So there are many different kinds of joints that we use. The table on the right on this screen shows 6 of the most common types of joints. We have, most commonly, is a revolute joint, or which you could think of this as a pinned joint, kind of. So if you remember back in one of the earlier activities where we made the square assembly and the triangle assembly, and we used pinned joints, well, in engineering, that is technically referred to as a revolute joint. We also have prismatic joints, which is a joint that allows one body to slide in and out of another body. We have spherical joints, which is a joint that allows a rod to move in any given direction. And other joints, such as the cylindrical or the screw joint. But we also have one that you may not think of, which is called the planar joint. So if we have 2 blocks sitting next to each other, when they're in contact with each other, that is technically referred to as a joint, and we call that a planar joint, right? Because if we hold the bottom block stationary and we move the top block relative to the bottom block, we can slide it in this direction, and we can slide it in this direction. And if we assume that gravity is going to hold the 2 blocks together, then it's constrained in the vertical direction. Now, I can't rotate this block in this direction, and I can't rotate it in this direction, but I can rotate it in this direction. So we've constrained 3 of the 6 degrees of freedom in this joint. So the table on the right shows you 6 of the common joints that we find in engineering, and we also shows how many degrees of freedom that each one of those joints allows. So now that we've talked about how we join 2 parts of a machine or 2 parts of a robot together using joints, we have to talk about how we would move those parts relative to each other. So we move parts relative to each other by using something called an actuator. An actuator is a device that converts one form of power into physical motion. So a good example of an actuator would be a hydraulic cylinder, for example. So if your mom or dad or grandparents may have a tractor with a front end loader on it, you might see them raise and lower that front end loader. And that's commonly done by using what's called a hydraulic cylinder. Hydraulic cylinder uses fluid power or fluid motion, and it converts that fluid power into linear motion. And so on the screen on the lower left, you see an example of a hydraulic cylinder. And in the middle, we can also use actuators to create rotational motion. So, for example, if you've been in a repair garage and you've seen a mechanic use a tool to take lug nuts on and off your car, he or she is using a pneumatic impact gun. And so, in that impact gun, there is a pneumatic motor that converts compressed air into rotational motion. And so, we also have electric motors. So, electric motors convert electrical power into rotational motion. And so, these are just three examples of common actuators found in industry. But in reality, there's all kinds of actuators out there. So, have your mom and dad or guardian help you go online again and just search actuators and see what types of things you can find. So, in our projects, here in a little bit, we're going to talk about how we're going to build a robot. And part of building that robot, you're going to want to move joints. And so, here's an example of one actuator that you'll probably use in your project. So these are just surgical syringes, just like you might find at the doctor's office. And we have connected the ends of these syringes with just a basic plastic hose. And so this is an example of how we can generate motion or convert motion from one body to another. So in this example, we're going to generate power by compressing air with one of the syringes, and we'll move the other syringe by using that compressed air. So if you see, notice I push down on one, how the other one comes up, and vice versa. If I push back down on this one. And so in your robot, you could use one of the syringes as an input to drive motion in the other syringe. So that's just one example of a really basic actuator. And so this one is really simple. And in industry, they can be very complex, very complicated. But at the end of the day, the basic idea is that you're taking a power source and generating physical motion by using the actuator. So on a robot, well, we typically use actuators to move the arms of the robot, usually via a hydraulic actuator or an electrical servo actuator or electrical motor. But oftentimes on a robot, we need to have the ability to pick things up, right? So in our example of picking up a box and moving the box from one Cartesian coordinate position to another Cartesian coordinate system, we would need some way to grab that box and then let go of that box. And so robots use something called an end effector to act as a gripper mechanism. And so we use end effectors to pick up and let go of parts. And so on the screen here, you see some different types of actuators. We have a linkage gripper. So look at the linkage gripper in this picture really close. Do you see anything there that looks familiar? Hint, hint. Look at the square versus the triangle body that we made earlier. So we can use linkage grippers. We can use vacuum to pick up parts. So for example, if we wanted to pick up a sheet of glass using a robot, we might use vacuum suction cups to pick up that glass. We have linear grippers. So if we have grippers that need to stay parallel to each other, we'll often use a linear type of joint to move those grippers back and forth. We can use magnets as a gripper. So if we have like sheets of sheet metal or metal of some kind. We can use magnetic chucks on the end of a robot to pick them up. So there are all kinds of end effectors in use in industry. In fact, many engineers have that as their full-time job, is just to design end effectors for robots. So what we'll do as part of our robot design, and we'll talk about here in a minute, is you will design a gripper to put on the end of your robot. So think about that. And so that is going to be our design project for Module 2, is we're going to build a robot using parts and pieces from your mom or dad or guardian's junk drawer. So one of the things you're going to do is design that robot. So use the same methodologies that we used in Module 1. So use the same design process. Use the same sketching techniques to sketch your ideas. And once you've narrowed down to a final concept in your mind of what you want, you'll draw out a 3-view print of your robot and put together a materials list for what you're going to use on your robot and how you're going to join those materials together. And then you'll do the same thing for the gripper mechanism. And so, again, come up with some different concepts, sketch your ideas in your notebook, narrow down to a final design, and create a 3-view sketch of your end effector that you'll use on your robot. And you'll bring all of those things to our in-person meeting so that you can build your robot. So as a part of our robot design, our goal is going to be to design a robotic arm and gripper that can move a weight from one spot to another location. So our weight is just going to be a ping pong ball, so nothing too heavy. Your robot, so our must-have, so these are the design constraints for the robot. It must have at least 2 of the 3 axes of movement. So it needs to be able to move in 2 of the 3 axes. So it also must use levers, joints, and actuators to build your robot arm and gripper. So it's a pretty wide open concept. Use your imagination. Go back and look at some of the ideas that we looked at already to come up with some concepts. And just like in Module 1, here are a few projects that people have done in the past just to give you an idea of what types of things have been done before. So let's take a look at those. So here we can see an example of a robot build where they've started to build the body of the robot. So that gives you some idea of how this person utilized some different types of materials. And here's an example of a gripper that someone designed. As you can see here, the use of the syringe as the actuators. And it looks like they use some popsicle sticks and some pencil erasers for the grippers. And then here's a robot that has both the robotic body and the gripper assembled together. And there you can see they've used a syringe as a linear gripper style. And so there you can see some just different examples of what some other people have done. So that brings us to the end of Module 2. So our next step will be to have our second in-person meeting. And during our second in-person meeting, you need to bring your prints for your robot and your prints for your gripper. Bring any materials that you're going to need, and bring tools and safety glasses, and be ready to build. And so just like in the in-person meeting for Module 1, we'll come into our in-person meeting for Module 2 You'll have all of your prints ready to go, and you should be able to hit the ground running and start building your robot as soon as we get there. So I look forward to seeing you in person, and I will communicate out to your parents or your guardian of when the in person meetings will be. All right. Thank you very much.